Now that we have the 3D Schrödinger equation, we're going to start solving it by separating variables. First of all, we'll remind ourselves what the Schrödinger equation is in spherical coordinates in 3 dimensions. Then we'll separate the radial and the angular coordinates. Then separate the two angular coordinates. And then take a look at the quantum numbers that we get and the separation constants and their relationship to operators. So, the time-dependent Schrödinger equation in spherical coordinates can be written like this. Minus h bar squared over 2m times the quantity 1 over r squared, partial with respect to r, of the quantity r squared times partial of psi with respect to r, plus 1 over r squared sine theta, partial with respect to theta of sine theta, partial of psi with respect to theta, plus 1 over r squared sine squared theta, partial squared of psi with respect to phi squared, plus v of r times psi equals e psi. Now this is difficult to solve unless we can find a separable solution, and the simplest separable solution is to separate the angular and the radial coordinates. So we define psi of r, theta, and phi as the product of two functions. One function is capital R of r only, and the second function is capital Y of theta and phi. When we make this substitution, we get the following. So everywhere we have a psi, we replace it with r and y. ry here, ry here, and ry here and here. The next step is to pull through the part of this separable function that is not acted upon by any of the derivatives in each of the sections. So in this section, we're going to pull the y through, because the only thing that acts on that this derivative acts on is the radial function. In these two, we're going to pull the radial function through, because the only parts that are acted on by these derivatives are the y functions that are a function of the angular variables theta and phi. So as we do this, we can now write minus h bar squared over 2m times the quantity y over r squared partial with respect to r of r squared partial of capital R with respect to r, plus capital R over r squared sine theta partial with respect to theta of sine theta partial of y with respect to theta, plus capital R over r squared sine squared theta partial squared of y with respect to phi squared, and then we have plus v of r times ry equals e times ry. Well, with this expression now, we're going to divide by ry. And when we do that, we get minus h bar squared over 2m. And then we have 1 over capital R squared, partial with respect to r of r squared, partial of capital R with respect to r, plus 1 over y r squared sine theta, partial with respect to theta of sine theta, partial of y with respect to theta. And then I get 1 over y r squared sine squared theta, partial squared of y with respect to phi squared. And in these two terms, we just have v plus v of r equals e. If we now multiply times the quantity 2mr squared over h bar squared, and then we bring the e over here, you can see what's going to happen. That's going to cancel this term in front, bringing it to the two terms here. But not only that, because you have an r squared here, you're going to get rid of this r squared, you're going to get rid of this r squared and this r squared. And the importance of that is that now this term here and this term here no longer have any dependence on the radial coordinate, r. And so we get 1 over capital R partial with respect to r of r squared partial of capital R with respect to r, plus 1 over y sine theta partial with respect to theta of sine theta partial of y with respect to theta, plus 1 over y sine squared theta, partial squared y with respect to phi squared. And then I have minus 2 mr squared over h bar squared times the quantity v of r minus e, all equals 0. Now, we can now group these into two separate terms. One term is the terms in red here, which have all the radial dependences. And the other term is the angular dependence part, which is all the terms in blue. And so we've now successfully separated this equation. We now have two terms. One in red, which is all r, all radial dependence, which is 1 over capital R partial with respect to r of r squared, partial of capital R with respect to r, minus 2 mr squared over h bar squared times v of r minus e, plus 1 over y times the quantity 1 over sine theta, partial with respect to theta, sine theta, partial of y with respect to theta, plus 1 over sine squared theta, partial squared of y with respect to phi squared. And all that is equal to 0. Now, because these are separated, the only way these can cancel to 0, or this guy can be the negative of this, is if they're equal to a constant. And in fact, the same constant. So they can cancel out because they're equal to a separation constant, which in this case, we will call L times L plus 1. And we'll find out why that is later. Now this gives us two independent equations, one radial and one angular. The radial equation is 1 over capital R d by dr of r squared d by dr by dr, d capital R by dr, minus mr squared over h bar squared times the quantity v of r minus e is equal to LL plus 1. And then we have 1 over y times the quantity 1 over sine theta, partial with respect to theta of sine theta, partial of y with respect to theta, plus sine squared theta, 1 over sine squared theta, partial squared y with respect to phi squared is equal to minus L times L plus 1. Now in this case, these are these are now no longer partial derivatives because there's no other functional form, no other variable in here. But these still have partial derivatives because we have both theta and phi that y depends on. Now, we'll get back to the radial function later, but we'll work on the angular function first. And the first step here is to further separate this in terms of theta and phi. So we're starting with this equation, which we had on the previous slide, and now we're going to assume a separable function. But before we do that, we're going to multiply everything times y times sine squared of theta. So that will cancel this y out here. It'll bring a y sine squared theta over here, and it'll cancel this sine squared theta, which is critical because that allows us to separate the thetas and the phis. When we do that, we get sine theta, partial with respect to theta, of sine theta times partial of y with respect to theta, plus partial squared of y with respect to phi squared is equal to minus L times L plus 1 sine squared theta times y. We now can rearrange this to group all the theta dependence and all the phi dependence separately. And that gives us sine theta, partial with respect to theta, times the quantity applied to the quantity sine theta, partial y with respect to theta, plus LL plus 1 sine squared theta times y, plus partial squared of y with respect to phi squared, is equal to 0. If we now assume that y is equal to two functions, capital theta of theta and capital phi of phi, we can now complete the separation. When we do this substitution for y and we carry out the part that doesn't depend on theta, we get capital phi times the quantity sine theta times d by d theta of sine theta d theta, plus capital theta, capital phi, times LL plus 1 sine squared theta. That is all the theta dependent part. And then plus capital theta d squared phi, capital phi d phi squared is equal to 0. All that remains now is to divide by theta phi, and we get final separation of variables, which gives us 1 over capital theta sine theta times d by d phi theta of sine theta d capital theta d theta plus LL plus 1 sine squared theta plus 1 over capital phi d squared capital phi d phi squared, and that is equal to 0. Now, the separation constant, again, for these two, is going to be called m squared. And so now we have two equations. We have one in theta, which says that m squared is equal to 1 over capital theta sine theta d by d theta applied to sine theta d capital phi d theta, d capital theta d theta, plus LL plus 1 sine squared of theta. And then we have minus m squared is equal to 1 over capital phi of d squared phi d phi squared. And these two equations are the ones we're going to solve next. Now, before we do that, which we'll do in the next video, we'll look at a minute at these three separation constants. So far, we've identified three separation constants of the 3D Schrodinger equation, each of which corresponds to a quantum number and an operator which commutes with the others, as it turns out. And this is important as we go further on. In this table, we have the separation constant over on the left, the operator that corresponds to that separation constant, and the quantum number that corresponds to that operator. And the first one is one that we're familiar with from the one-dimensional quantum mechanics problems we've done, and that is the energy, the separation constant E. The operator is the Hamiltonian, and the quantum number is n for a discrete system. The next one is this LL plus 1, which allowed us to separate the radial and the angular equations. Turns out that the operator that we'll be looking at here is the angular momentum squared operator. And the quantum number is L that's associated with that operator. And finally, the m squared, which separates the two angular components, corresponds to an operator L sub z. So the z component of the angular momentum, and the quantum number is m.